Welcome, everybody. Today, our seminar speaker is Heather MacLean. She's a professor in civil engineering at the University of Toronto. Heather has done work on conventional and alternative energy systems. A lot of her work focuses on modeling the techno-economic and environmental performance of bioenergy systems, both for transportation fuels and for electricity production. She also works on unconventional fossil fuels. And she's done some alternative fuels and propulsion systems for light-duty vehicles, so things like electric vehicles. She has a lot of degrees. She has an MBA, a master's and PhD from my alma mater, Carnegie Mellon, and her work is really interesting. It incorporates elements of mechanical, environmental, chemical engineering, as well as economics and public policy. So without further ado.
Thank you, Corinne, for the kind introduction, and I'm really pleased to be here and thank EBI for the invitation. And it's great to come to California on the only rainy day of the year. I was trying to get away from that cold weather in Toronto, so I got the warmer weather, but not the optimal sun. But being from the east coast of Canada, I'm used to the rain, so it has not deterred me, and it was nice to have a walk this morning in the warmer weather. So I'm going to talk a little bit about my work over the last number of years, sort of go through a tour across the life cycle from feedstock production to conversion and then finally end use of a number of different bioenergy systems. This work has combined, as Corinne has mentioned, some techno-economic analysis, sometimes some feedstock supply aspects. But today, due to the time constraints, I'm going to focus mostly on life cycle perspectives from the environmental perspective and particularly greenhouse gas emissions across these different case studies. And my first trip out here to Berkeley years ago as a graduate student was to meet Lee Schipper at the lab and to talk about transportation and energy aspects, and meeting such an eclectic person as him motivated me to work in sort of an interdisciplinary type of area. So this was working, so let's try this. Everything was working when I tried it, but
is it working on the keyboard?
no.
Of course not.
I tried it just before.
Oh, that makes beeping noise. Nice. Adam, if you're hearing this, because I would really rather not restart your whole computer, but is it the no, it's frozen. So
I said the mouse was moving.
Mouse, but nothing else. So.
Okay, let's try.
Yeah. Nope.
Okay.
Nope. Yeah, those are the tricks on there too.
Okay. Yeah, let's do and no escape. Alt tab. Let's see if that works.
Oh, so is it the other PowerPoint?
Okay, we're there. Okay, let's do. Let's start the slideshow again.
Yeah, that works. Maybe it's not here too long.
Let's see. There.
Thank you, Anna.
Thank you. Two people to fix things up here. So as I mentioned, I'll talk a little bit about the evolution of life cycle approaches specifically for bioenergy over the time that I've been working on these. I started around the late 1990s, I guess, early 2000s. I'm looking at life cycle and bioenergy systems. And then sort of this tour across the life cycle looking at feedstock case study on forest carbon implications, looking at the importance of enzymes in biomass conversion process, and then a variety of pretreatment and co-product options, and then finally ending with the sort of role of a comparable end product being light-duty vehicles in this case study. And then a slide on lessons learned and some future insights. So as we all know, you're an audience who's very familiar with this, but due to the complexity of bioenergy systems, you need sophisticated analyses, and we need analyses that go beyond a traditional life cycle assessment approach, which focuses really on environmental aspects. And in most life cycle studies of bioenergy systems, the dominant sort of metrics that have been investigated are life cycle energy use and greenhouse gas emissions, partly because these are perhaps the more straightforward ones to look at, but we need to move much more broadly beyond this and not just have this exclusive focus. We need to look at the technical feasibility, obviously, financial, economic aspects, social aspects, supply aspects. So in some of our work, we've been trying to integrate some of these other tools that could capture some of these aspects in with life cycle assessment. However, it's not really clear how optimal or how feasible it is to integrate some of these tools and whether the results coming out of these are providing accurate analysis or not. So life cycle assessment, as I've mentioned, focuses entirely on the environmental aspects. Some people are incorporating some social aspects into life cycle assessment, but a traditional life cycle assessment does not include really the detailed technical aspects or the financial aspects, and sort of glosses over aspects such as temporal and spatial facets that really come into play when you're thinking of a broader sustainability perspective. And so the case studies I'll look at today start off with the feedstock production options, fuel production, and if we're using those in a transportation setting, often we refer to as well to pump, and then use in the vehicle, often referred to as pump to wheel, and then the sum of those, the well to wheel. So traditional uses of life cycle assessment were to inform product development, to look at not transferring burdens from one life cycle stage to another, to try to avoid suboptimal decisions, and then to inform some sorts of policy development. But more recently, life cycle assessment has been sort of called upon at a higher level, more of a task, to inform funding agencies and investors over which types of processes, new technologies should be funded. So our research group has done a number of consulting projects where we've been asked to analyze the emerging technologies, to project what would be occurring at full scale of these technologies, and then sometimes funding decisions have been made based on that. And there's a lot of challenges to doing that, but it is being employed in that type of area. And as well, you're all here in California, so you're very familiar with the California Low Carbon Fuel Standard, where the carbon intensity on a life cycle basis of the fuel production process compared with the gasoline baseline is being used to enforce policy and can have significant financial implications for companies selling fuels into the state. So we've participated in some of those discussions as well with the California jurisdiction as well as others in Europe and in Canada. So back when I started working in life cycle assessment in the late 1990s, there were very few journal articles that were published in the field of biofuels life cycle assessment. There's been sort of an exponential growth of these articles, but the field is still really at a fairly immature level. It's an emerging field. There's a lot of lessons still to be learned. There's perspectives in the field, opinions in the field that are sometimes very strongly held about what is right, what is wrong to do, as in every type of field, but we have to look at really improving sometimes the quality within the field and the maturity of the analysis within the field, because sometimes there's still some surprises that get published, which happens in every field, but sometimes these are not necessarily justified based on the analysis that is done. This is kind of a busy table, and I won't go through it in great detail. But there's been sort of this evolution of life cycle approaches, and sort of the traditional approach in the middle column here, where life cycle assessment is best placed to look at historical or current production, but more and more so is being called upon to evaluate emerging technologies and all of the limitations associated with that. And so we've tried to make progress in this regard in a number of the analysis we've done, but there's a lot of uncertainty associated with these analysis and sometimes not always transparently presented. The scope, as I mentioned, has typically been energy use and greenhouse gas emissions. Other studies, there have been some good work, including here, on more metrics that have been looked at, but there's still a lot of progress that needs to be made in integrating life cycle approaches and how best to do so. Feedstock has often been viewed with this carbon neutrality assumption, where the assumption that the bio-based carbon doesn't contribute to atmospheric carbon dioxide emissions, and whether this is a valid approach or not. And so there's a lot of emphasis now on land use change and quantification of feedstock carbon implications. So I'll talk about one case study in that. And then biomass conversion processes often were portrayed sort of as black boxes, sometimes due to the proprietary or secretive nature of the technology, but in other cases because the life cycle analysts really weren't that expert on the technology. And so a lot of our work has been on more detailed chemical process modeling of multiple options, which I know has been ongoing in EBI as well. And then the lignocellulosic ethanol production often was modeled with a single co-product being electricity, but there are multiple co-product options with considerable implications for environmental and financial metrics. And then the final case study I'll talk about is the simplified treatment of the end use of the product and attention to vehicle comparability or to comparability of the end product and how that can impact some of the results. Another thing that I'll be guilty of today is presenting some point estimates. But there is a lot of emphasis these days in life cycle assessment on variability and uncertainty analysis. We have some current projects where we're trying to sort out the actual variability component versus the uncertainty component. And there's been a lot of limitations sort of with point estimates and even ranges that have been produced. But there's also a lot of challenges, as I mentioned in some of my meetings this morning, of these very broad Monte Carlo analysis, which I'm not sure are really capturing in a better way, sort of really the reasonableness of the estimates that are portrayed. So starting with the feedstock case, and as I've mentioned, a lot of biomass and bioenergy systems have been, a lot of their greenhouse gas reductions compared to fossil-based systems have been in large part resulting from the assumption that the bio-based CO2 emissions don't increase atmospheric CO2. Whether this is a reasonable and accurate assumption and in what cases it's a reasonable accurate assumption, I think needs to be revisited. So the first paper was one done with a prior PhD student of mine, John McKechnie, who came up with many of the ideas within the paper. He's now a faculty member at the University of Nottingham in the UK. And so what we wanted to look at was the sort of trade-offs between the harvest of the forest material, and this was a forest in Ontario. And in Ontario, as you're familiar with the climate there, these forests do not grow quickly as on the west coast. And so it can take up to 100 years, 60 to 100 years to sort of regenerate a forest after a lot of harvest. And so we wanted to look at the implications of taking into account the forest carbon aspects related to additional harvest to produce bioenergy versus the reductions that you were getting from displacing the fossil-based fuels. We applied this to the case study of co-firing of biomass wood pellets in coal-fired generating stations in the province, and we collected data from the utility company on the actual sort of operations of these facilities and reductions in efficiency, et cetera, operating on the wood pellets. So we started by looking at the biomass production, which was in a provincially managed forest called the Great Lakes St. Lawrence Forest region. It represents about 20% of the provincially owned forest in the province, which is the vast majority of forests. And one of the interesting aspects of it was that even with this 5.4 million hectares and 1.8 million oven-dried tons of woody biomass plus some residues that could be harvested, we were only going to be producing about 2.2% of the electricity within Ontario that was required. And so even though a very, very large amount of biomass, we weren't producing really a substantial amount of the electricity. But the main focus of the case study was to look at the trade-offs between the forest carbon and the fossil fuel displacement. So we collected data on pelletization, transported the pellets to the electricity generating station, and then used them at a 20% energy basis co-firing rate. So we set up a few different baselines due to the downturn in the forest industry. There was additional wood that was available under the sustainable forest management plans that was not being cut. And so we had a current harvest baseline where we were only producing conventional wood products. We then had another scenario where we were collecting residues within the forest. They're traditionally left to decompose within the forest. And then we also had what we called a maximum allowable harvest, where we were harvesting additional standing trees, the round wood from the trees, for bioenergy. And this was all allowable under the sustainable forest management plans. The difference in the carbon stocks between the scenarios either 2 or 3 and 1 was then allocated to the bioenergy product because of the increased harvest and increased removal of the carbon from the forest. So we took a forest level perspective rather than a stand level perspective in this. So within the forest, there were thousands of different stands at different stages of their life. And so at a steady state, the removals in one stand could be compensated for by regrowth occurring in the forest. But at steady state, this carbon could be reaccumulated in as little as 1 year. But when we increase the harvest rate for the bioenergy production, we were now going to be shifting the forest to a new sort of lower carbon stock equilibrium over time. I'm not going to describe the stand level, but we can discuss that if, yes?
I may have missed something, but are these experiments that you conducted on the forest, or is this a model that you have about?
This is a model that we have, yeah, coming up in the next slide. So, yeah. Coming up right here. So what we did was we took the conventional sort of life cycle perspective, where we looked at the different activities that were in that sort of pictorial diagram that was presented earlier, where we had the biomass harvest, transport, the bioenergy production, and then the use. And then we calculated the greenhouse gas emissions excluding the bio-based CO2. So these were associated with the pellet production and the electricity generation. And then we added on to this the forest carbon model. This is a model that's maintained by the Ontario Ministry of Natural Resources. It's a modified version of the 4-carb model, which is a US-based model. And it's modified for the Ontario situation and estimates the carbon stocks in the forest over the 100-year time period. And so what we were looking at was the sort of balance between the removals of the carbon versus the accumulation in the atmosphere. And then we were attributing these bio-based emissions to this system above. So what we did was to integrate the life cycle assessment and forest carbon analysis, which had a couple of challenges associated with it. And one of the main ones being that the 4-carb model works over the 100-year time period, whereas life cycle assessment works over a functional unit basis, and obviously these are not equivalent. So we had to make some simplifying assumptions, which we revisited later in the paper as to how valid they were to do. So what we did was we calculated the life cycle emissions on the left-hand side, excluding the forest carbon, to be about 90 grams of CO2 equivalent per kilowatt hour. We then looked at what if we were just combusting the coal in the generating station, which was about 1,000 grams of CO2 equivalent. And then initially, with the increase in the harvest of the forest, we ended up with about over 1,000 grams of CO2 equivalent in the bio-based system. Now this changes over time, and I'll talk about the standing trees and leave the harvest residues for discussion later if of interest. So we have the emissions associated with the harvest within the forest, so positive here being emissions and then reductions in emissions being the negative. So this is showing the considerable increase in emissions associated with changing the rate of harvest within the forest. You would expect this curve to not have this sort of blip in the middle there, but that is related to natural disturbance aspects, past forest management decisions, etc., so that it in reality rather than sort of in theory how these things work, we ended up with the blip in managing in the modeling. Then if we add on here the light blue line at the bottom, this is the reduction in emissions associated with no longer using the coal in the generating station, and which is showing to be linear over time. And this was the very simplified assumption that technology wouldn't be changing, that we could be using these pellets over the 100-year time period. So with lots and lots of limitations, but we weren't really able to figure out an assumption to get around this sort of continual harvest and use of the pellets over the 100-year time period. So something to be sort of figured out in the future work. The blue curve in the middle is the net of the two. So the overall result is that by taking into account the forest carbon perspective, we have a delay in when the emissions mitigation starts, and the curve crosses there at about 38 years. And we also have a reduction in the actual mitigation associated with the use of the wood pellets compared to if we had not, if we had assumed a carbon neutrality aspect. So I think this sort of repeats what I've just said about the sort of initially we exceed the avoided fossil fuel related emissions, temporarily increasing overall emissions, but in the much longer term, after 38 years for the standing trees or 16 for the residues, then we're ending up with our reductions. So ignoring this complex relationship between the carbon stocks sort of was overstating the greenhouse gas mitigation performance of the bioenergy system.
Details about how the forest was managed? I mean, was it just natural regeneration? Was it clear cut? Was it,
there's some clear cutting that takes place. There's some selection cut, and there is some shelter wood harvest of the forest. And some of it is naturally regenerated and some of it is replanted, depending on how the stands are harvested. And they're managed by different managers of the system as well.
It seems to me those things have different impacts, and I'm surprised you didn't try to dissect.
We didn't have as much detail on those aspects and exactly where they were occurring as we would have hoped. There was a lot of aggregation within the model, but the model does take into account those sort of averages of the amounts that are clear cut versus shelter wood versus and regeneration and natural disturbance and things. There's very little natural disturbance in that forest. It's a good point. Thank you. So this work was done for Ontario Power Generation, who was there's a regulation in Ontario where they have to stop using any coal for electricity generation by the end of this year. And so they were looking at options, not just the co-firing, but exclusively using pellets in their generating stations. And obviously when we came out and included the forest carbon aspects within the analysis, they were not as pleased as when they just had the 90 grams of CO2 equivalent for the result. And so they made some different decisions about where they would source their biomass from based on the analysis. So moving on along the sort of tour across the life cycle, I'm going to cover briefly another couple of case studies related to the fuel production. And the first one is looking at the role of enzymes, specifically with respect to biochemical conversion and lignocellulosic ethanol production. And when we began this work that was begun in the late 2000s, there wasn't very much focus on enzymes. They were not included in any of the life cycle models, really. I think they were included maybe in one of the European models, but the Greek model of the Department of Energy, the Canadian model, were not including enzymes within their analysis or process chemicals. And we also didn't really know too much about the production costs because this is proprietary information. So an initial paper back in 2009 with one of my prior PhD students, now a professor at Drexel University, Sabrina Fatari. We used pretty rough assumptions. There was very limited data available. And we came up with that the enzyme contribution could be about 30 to 35% of greenhouse gas emissions, but it was based on fairly rough data. And so then we did a more detailed analysis published last year, where we looked at both on and off-site production of enzymes, so on-site at the ethanol facility, and then off-site where the enzyme production would be servicing various different facilities. We looked at different ethanol plant capacities, different yields of cellulase from the assumed glucose carbon stock, and I'm going to be mostly presenting results for the 90% yield on the more optimistic side, so that's why that's highlighted. And then we looked at enzyme loadings, different loadings as well, and we looked at the financial metrics, but I don't have too much time to cover those today. So we were looking at getting the glucose from a corn wet milling process, and so we included and allocated to the enzymes on a mass basis some of the corn farming inputs as well as the wet milling aspects. We then had the glucose production. The cellulase production we modeled within the Aspen Plus chemical process modeling software. And we started with one of the NRail models for this, but then we made some modifications to the model, and as well for the off-site production process, which wasn't included in the model, we had to add the purification steps, transportation steps, etc. So going right into a couple of the results, we see the results for both the on-site and off-site for the loading rate and the yield that are noted here. And common to both the on-site and off-site, the glucose production, due to the fairly energy-intensive greenhouse gas intensive corn production and wet milling process, these contribute substantially to greenhouse gas emissions. And then as well, the electricity, which is down here, which is used to run the process equipment within the enzyme production facility, was fairly substantial as well. On the off-site production, due to the downstream purification aspects, there's additional nutrients, chemicals, etc. that are required, and so this comes into play as well. So slightly higher emissions for off-site than on-site production. However, there could be economies of scale related to the on-site versus off-site production, and so it's not necessarily the apples-to-apples comparison to just compare on versus off-site. One of the other aspects increasing the off-site emissions is that there was an assumption that we would lose some of the cellulase in the purification process. We assumed a 15% loss of that, and so that has implications because we're getting a lower yield in the off-site. So what we wanted to do was sort of to put this in perspective and what proportion of life cycle emissions would enzymes represent. So we took a range of published studies that excluded the contribution of the enzymes, and those went from about 500 to 900, so almost double in grams CO2 equivalent per liter of ethanol. And if we were then to add on the emissions associated with the sort of at the lower bound, the 3 milligram and the 90%, then we had between a 10 and 25% increase if we were to add these on for life cycle emissions. At a higher loading, this could be up to about a 75% increase in the ethanol life cycle emissions compared to not including the enzymes. We had some discussions with California over the inclusion of the enzymes within the low carbon fuel standard with some different producers as well. And then one of the major enzyme manufacturers did provide some validation of both the cost numbers that we had as well as the greenhouse gas emissions. But there is a lot of uncertainty within this, and some of the challenges in doing this analysis are noted here. Yes?
So when you make assumptions about converting the amount of carbon that goes into the enzymes to a comparable unit for the amount that's going into the overall process, how often are you assuming that they're replacing the enzymes? Like they have to throw away the enzymes at some point and then get new ones.
Right.
So what assumption about frequency are you making there?
To be honest, I can't recall.
Okay.
So I can look that up for you.
I assume it's all batch. You were assuming a batch process.
Yes, we're assuming batch.
Thrown away
Yeah.
3 times.
But
not
you
recycled.
get some amount of productivity out of each enzyme, which you have.
But that's what she's included when she says 3 mg per gram.
Okay.
yes, that part is included there. Yeah. So what we concluded from this was that even at the fairly low loadings, that the enzymes could be fairly significant. And when we started some of this work, the enzyme aspects were not included in the life cycle estimates in the models. And so when producers were saying that they were going to lower enzyme loading or be more efficient in production, they were not able to really get credit for this because the value is currently at 0. And so we can't sort of give a credit for a negative. And so seeing some improvement, at least having some basic estimates within the models was an improvement in how this is being treated. However, as I mentioned here, and I won't go through all of these, but there are a number of challenges. There's a lot of uncertainty in some of these estimates, and obviously the enzyme data is fairly proprietary, so difficult to get the exact numbers. So another fuel production case study. This one was looking at a variety of different pretreatment processes, which some of you are probably much more into and in looking at in detail than we were. But what we did was we took pretreatment data from different companies and from NRail. We obtained their Aspen models, and these Aspen models typically had only electricity as a co-product, so we modified the Aspen chemical process models to look at a series of different potential co-products. Most of these are not co-products that were being produced, but we looked at a variety of these, and we tried to sort of optimize the production of these for within a consistent framework where we were modeling these biorefineries. And this work was initially started by Tim Shen, who was a master's student at the time, and then continued by Mohammed Pourvafrani, who was a postdoc working in the research group. So we looked at a common biorefinery producing using 2,000 tons per day of corn stover, and a typical biochemical process for producing lignocellulosic ethanol. And the co-products we looked at were diverting some of the sugars to produce xylitol, a sweetener, and as well recovering some of the proteins, assuming that they could be recovered and at the purity for displacing some animal feed. And then we also looked at electricity co-product, the conventional one, and as well producing lignin pellets and using those to displace coal in generating stations producing electricity. So these different pretreatments have different inputs, different effectiveness in conversion of the sugars, and the different co-products have different implications for things that they might displace in the market, and as well different implications potentially for yield and other aspects. So this was the set of pretreatments that we looked at. We looked at the dilute acid hydrolysis, which has been probably the one most commonly modeled, particularly in life cycle studies. We obtained the Aspen model from NRail. We looked at the AFEX, the ammonia fiber expansion, and we obtained a model from MBI. And then we looked at an autohydrolysis process. We obtained the information on this from Mascoma, which was previously SunOpta bioprocess in Canada. The electricity co-product was looked at for all of the different pretreatments. The pellet option was also looked at for all of the different pretreatments. The protein aspect was only looked at for the AFEX, and this protein production allowed some of the ammonia to be recycled using this option, and so therefore that was viewed as a feasible co-product. The dilute acid would be too strong conditions for producing the protein co-product in our view, and so therefore was not considered optimal. The autohydrolysis, we possibly could have produced the protein in this, but we expected that we would require supplementation with ammonia, and because of the high GHG and energy cost, I'll call it, of adding the ammonia to the Mascoma process, we decided to not look at the protein in that case. The xylitol option was only looked at with Mascoma because they were proposing a facility that would use a Xylitol Canada proprietary process to convert the xylose sugars to xylitol. And so therefore we looked at that option, and we combined it with an electricity co-product and a pellet co-product. But this did reduce the yield of the ethanol in the autohydrolysis process. So in life cycle assessment, co-products can be treated in different ways, and how you treat these co-products often very significantly impacts the results and your greenhouse gas emissions. The most common method specified under the ISO standard for life cycle assessment is to use a system expansion or displacement method. This is also specified generally and most often used for bioenergy systems and specified under the Renewable Fuel Standards US EPA. So this is the option that we used in this study. However, we've done some other work where we've looked at the implications of displacement versus energy bases, and there's very, very substantial differences often in the results, and so this is something that one needs to be aware of. So in this displacement method, some of you are probably familiar with it. Essentially, the ethanol product is designated as the main product, and then a credit is given to production of other co-products of this process, such as the xylitol in this case, and we're going to subtract off the emissions associated with the production of the conventional sugar in this case, and on a mass equivalent basis of the xylitol, and we're now going to get a credit to the cellulosic ethanol essentially. So I can go into more detail about that subsequently, but just to show sort of what was assumed to be displaced. So if we produced electricity as a co-product, we assumed that we were going to displace the Midwest average US Midwest average grid mix. If we were producing the protein, then we were displacing soy protein. And then if we were producing the lignin pellets, we were going to be displacing the coal. And so one thing to note here is that what you assumed you're going to displace and how GHG intensive it is has significant implications on our results that we will see, and much more significant implications than the differences in these pretreatments. And so the big difference between the electricity here and the lignin, even though the Midwest US grid has a lot of coal in it, there's a significant difference in your co-product credit because you're displacing the coal, which is about as carbon intensive as you can get, as you know. So the choices of the different pretreatments, the co-products impacted the yield due to differences in their efficiencies in sugar conversion, but also with the xylitol co-product, where we were now diverting that xylose from the ethanol production, we had a substantial decrease in our yield down to about 200 versus 300 and up liters per dry ton. The dilute acid pathways had higher ethanol yield, a bit lower well-to-wheel energy use, but similar well-to-wheel greenhouse gas emissions when producing the same product. And this is a bit of a busy figure, but I'll try to point out a couple of points on it. And I always said to my student, I don't like these abbreviations here at the bottom, but we couldn't really figure out how to come up with something easier to interpret. So this was comparing reference gasoline pathway, which is on the left-hand side, which has about 95 kilograms of CO2 equivalent per megajoule of fuel produced. And then these show the dilute acid pathway with either the electricity co-product or the pellet co-product. And the main difference, as I mentioned, between these is that you get a much, much larger credit for displacing the coal than you do the average grid mix. And so that's the difference really between these two pathways. If you move on to the apex, you can see that for the same co-product, and this applies also to the autohydrolysis, for the same co-product, the results are fairly consistent across the different pretreatments. So if you're producing electricity, in either the dilute acid, the AFEX, or the autohydrolysis, results are fairly substantial. Fairly similar. Same with the pellet option. So the difference is occurring more due to what you're displacing than the difference in the pretreatment from a GHG perspective. Now, this may certainly not hold when you're talking about a financial type of analysis. The highest emissions are occurring where you're using the AFEX and producing the protein and electricity. You're getting a lesser credit for offsetting the protein, and you're also having some higher emissions in that case. If we move over here, the lowest emissions occur where you're producing the xylitol and the pellet, and this is driven in a lot of cases by the pellet aspects, because you do have a higher well-to-pump green bar there, which is the production associated with it, but because you have this very large credit associated with the pellets, you've got the lowest emissions here. So in summary of this, there were similar emissions across all of the pretreatments when producing the same co-product, but key factors that could change this result or that this result depends on are amount of chemical use in the dilute acid process, how much ammonia could be recovered in the AFEX process, as well as some of the ethanol yields. And because most of these processes are not mature processes or being used at large scale, many of these questions remain to be answered and could have implications for results. All of the pathways could result in reductions of more than 60% compared to gasoline. We had a fairly wide range of emissions results. And so if one is interested in the biofuels classifications under ESA, when assuming the co-product displacement method, which is often assumed in making those calculations under ESA, these could meet the cellulosic biofuel classification. If you were to switch to an energy basis or other basis, it's likely that some of these options would not meet that. And the last case study, which I'm going to go through fairly briefly to leave a few minutes for questions. This is where we were looking at the importance of a comparable end use. And so one of my current PhD students, Jason Luke, was particularly interested in vehicles. He has a mechanical engineering background. He's sort of interested in bioenergy systems, but more so in vehicles. So he wanted to look at the implications of different vehicle choices and looking at liquid fuel use, namely the lignocellulosic ethanol, versus bio-based electricity. And so he worked with Mohammed, the postdoc, in taking some of the prior developed Aspen models for the ethanol, developed a new model for using the Rankine cycle for the biomass-based boiler for the electricity generation, and then he modeled some of these different types of vehicles, and he focused on the quantity of biomass available and how far you'd be able to travel based on it. He used the autonomy vehicle modeling software, which is out of Argonne National Laboratory, because he wanted to, rather than using sort of vehicles on the market, he wanted to model vehicles that had common acceleration times, common space requirements, number of passengers, trunk space, etc. So we took some of our prior models, the hybrid Poplar and then the Mascoma autohydrolysis pretreatment process, and we looked at producing the lignocellulosic ethanol and using it in either conventional internal combustion engine vehicles, hybrid electric vehicles, or plug-in hybrid electric vehicles. Then for the electricity, we took the hybrid Poplar, common feedstock, used the Rankine cycle to produce the electricity, and then looked at the plug-in hybrid and the fully battery electric vehicles. And a few more specifications from Jason on how this was done and the labels on them. But so what did we find? Contradictory to some of the prior studies, we found that there was fairly similar life cycle greenhouse gas emissions associated with the use of the liquid fuel versus the electricity. So some of the prior papers had often showed substantial benefits of moving to the electric vehicle options. We found that there could be similar greenhouse gas emissions and fossil energy use across most of the vehicle platforms. These were all substantially lower than the gasoline, and we used, in this case, the US average grid mix for the electricity. We found that there were the fuel production efficiencies versus the vehicle efficiencies could largely offset each other. So if you had a low efficiency of electricity production, then you had a high efficiency of electric motor, for example. These were offsetting each other in all of the pathways. So we compared our results with a couple of the prior studies, one by Campbell that had been published in 2009. And Campbell essentially showed that you could drive considerably further in an electric vehicle than you could in the ethanol-fueled vehicle. So this is in vehicle kilometers traveled per unit of life cycle total energy use. And in our analysis, we were at our lower bound, we were showing fairly similar performance for both the ethanol and the bioelectricity. And then we looked at sort of a sensitivity analysis, which moved us slightly ahead with our ethanol. And what we found was that there were some differences between the two studies. One of them was that the vehicles that were assumed by Campbell, their team wanted to model vehicles that were actually sort of on the road. And so they looked at a 4-passenger highway capable, well, some people might consider it highway capable, but the Suzuki Swift, hopefully there's no Suzuki people around here. And then they had this sort of what we wouldn't call highway capable, at least not in the California or Toronto area highways, the 90 kilometer per hour maximum Ford Think City. And so while Campbell stated that the electric motor was about 3.2 or something times more efficient than the engine, these vehicles actually, some of the differences were up to about 5 times more efficient. And so then we had this computer simulated mid-size sedan with sort of the equal aerodynamic drag and acceleration time, size, etc. And this had fairly substantial implications for the results. And so we just wanted to make a comparison of to show that the importance of looking at sort of apples to apples, not that sort of one aspect is necessarily better than the other. It depends on what kind of question you're trying to answer. But I think we need to be sort of transparent in our assumptions and what's causing results to happen, because sometimes out there in the media or in the general public, people are getting the wrong message from some of the studies that are getting out there. That's the detailed results there, but I won't cover those. So just to end, and thank you very much for your attention. I know I've covered a lot of different topics, but life cycle assessment, reflecting back on working many years in it, it helps us structure our thinking about some of these complex environmental issues. But it does remain an emerging field where there's a lot of work that's still yet to be done. And I think we have to be aware of the limitations of life cycle assessment and where it should be used, where it can be best used, what type of information it does provide. And then moving forward in assessing bio-based systems, I think we need to focus on broader systems approaches. We have to make sure that people doing these types of studies are collaborating with experts in the field to make sure that the technical aspects are being done correctly or as correctly as possible, collaborating with experts in feedstocks, and having an open dialogue on how best to address some of these issues. And I think that these are aspects critical in moving forward with the field to provide transparent analyses. I think also we need to look at trade-offs between sort of model complexity versus model simplicity and transparency in doing these types of studies, because sometimes we're getting buried within sort of the models, and and we're not able to do appropriate verification and validation of these. So all of this work wouldn't have been possible without the people within the research team, a few key collaborators and students, either current or prior, who have worked on this. And then as well, we had some key sponsors for the work as well. And I'd be pleased to have any questions in the remaining time. And we have a question from Tom.
Thank you very much. I thought you brought up a lot of really interesting points, and I just want to throw it out for a little more comment. Because you alluded early on about uncertainty and variability, and then I think you said Monte Carlo, and I will agree Monte Carlo doesn't help you. I mean, it just creates a mess problem. And dealing with uncertainty means understanding scenarios. So go to the end of your talk where you showed how important it is to know your scenario and drill down to what's going on. I think one of our problems is, as much as we try not to look backwards, we still seem to be handicapped by the technology we know and not what is likely to happen.
Right.
And I think some of this traces to, both of these issues trace to understanding how to use scenarios. I don't know if you have more thoughts on that issue of really,
That's a tough first question there.
That's kind of where we end up in all of these issues are because we fail to, we don't have a good crystal ball, but I also think our tools tend to make us want to pick our favorite scenarios or what we think is a likely scenario, which would be totally wrong. But,
right. Yeah, I mean,
in terms of that uncertainty.
Well, it's a good question. Nobody can sort of predict what's going to happen in the future, and scenarios are sort of at best what we feel might be reasonable sort of projections for the future, the things that could, potentially happen, but as well sort of if those types of things happen, what are the implications of them? And perhaps that's more the sort of lessons learned of looking at a broad range of scenarios and not being sort of handicapped by choosing the ones that we know. But obviously we're sort of the same with our co-product analysis. For example, we were limited to what we were selecting based on potential feasibility, but as well data availability. And so I think always in the sort of life cycle approaches, we're very limited by what we feel are data that can be reasonably available and how to make assumptions about filling in gaps or how to put ranges on variables. And so that's, I think, what's leading people to put these Monte Carlo, broad ranges, and somehow that is being perceived by some reviewers, at least, as being something necessary in papers. And if you're not doing that, somehow now this is becoming added because the reviewer has now asked for it. And it's been difficult to push back, I guess, and to move beyond that. But I think we need to do so. But who's first? The gentleman in the red. Yeah.
I think that you really emphasize the importance of uncertainty, but one thing that's clear to me is that a lot of time is related to what Tom said. You really speak about dynamic phenomena. Mm-hmm. So when you look, I'm an economist, so what people really look, they look at the number.
That's right.
And the number that you give us generally is the number today. Well, there are processes of learning by doing and improving use in the future. Mm-hmm. And to me, you may impede the technology by showing that today it has some sort of a problem if it has a huge potential for improvement.
Right.
You take into account potential to improvement because how much close you are to the limit versus what we have now, that's what we have, and let's make it a little bit more.
Yeah, we've done our best in some of the evaluation of the emerging technologies to look at what people have projected, percentage of theoretical efficiency, how close they are projecting that, and some of the projections in the future were shown to be very overly optimistic, so going too far in that direction. But in our evaluation of some of these different pretreatments and co-product production, we have taken sort of the basis of the models today, but in many cases those are not able to achieve those today. And so with my colleague Brad Seville in the Department of Chemical Engineering, he does a lot of consulting for companies developing these types of technologies, and so embedded in some of these, but not very transparently, I will admit, are sort of aspects associated with what you're mentioning. But the formal sort of learning by doing and economies of scale kind of aspects even, I think have been fairly sadly lacking from what people have done in the field really. So people either have been overly optimistic and not been very clear about what has been achieved to date and how they've now projected over here, or they've taken something that is kind of a static approach and not really taken into account what's the possibility for the future. But it's an important point, and we need to learn from these economists in this way. So, yes?
So early on you alluded to accounting for multiple variables, for example, cost.
Right.
And so one thing that I've noticed whenever you see like actual progress in environmentalism is places where the environmental concern kind of coincides with the cost concern, and people make the step in the right direction, right?
Right.
So I was wondering if, for example, in the case of where you were evaluating like lignocellulosic fuels, whether any of these particular scenarios not just improved the GHG emissions, but also were cost savings in some way. If that's a thing that you guys have looked at or something that anybody is looking at.
That was sort of our next step with our co-product work, was that we were looking at this broader set of co-products because of the challenges of the financial viability, essentially, of the ethanol production sort of commodity type of product and the electricity as well. And so we were looking at sort of what would be the potential for financial benefits of having some of these alternative co-products. And so we've done some of that, but we didn't get there yet on the co-product side. But we were recently working on a process looking at a citrus waste biorefinery process, and the value of the limonene co-product was very critical to this. And initially we couldn't really find very much data to support sort of the financial analysis on it. And so when I reviewed the paper of my postdoc and on Collaborator on this, we were getting a return on investment of 40% or something, and I said, well, we should be out there, investing in this thing, if it's looking that attractive. But then I sort of said, well, what's causing this to be so attractive? Well, we couldn't find very much data. It's really dependent on this co-product value, and we don't really have any idea what that reasonable price is. But you can certainly end up with way out of line sort of estimates for the financial analysis if you're not able to support it with the sort of reasonable product prices. So that was kind of a lesson learned on that. But definitely the financial sort of analysis and looking at sort of more attractive scenarios has been part of it. And then the enzyme work, we did look at costs of the on-site and off-site production, so I could send you that paper if you're interested. Any other questions? Anybody in the back questions?
I think at this point we'll
finished?
any further questions happen over lunch, so let's thank Heather one more time.